Welcome back to The Explainer. Today, we're diving into something that's literally hiding right beneath our feet. We're going to explore the hidden infrastructure that physically connects our entire planet. I'm talking about the incredible journey of transforming raw, solid glass into the high-speed optical fiber that actually powers our digital world. So, let's just dive right in. Here is our roadmap for today's factory tour. We'll cover 1. The magic of glass. 2. The 5 stages of creation. 3. The physics of light. 4. Single versus multi-mode. And finally, 5. Why fiber beats copper. Let's get started. Section 1. The magic of glass, the backbone of the network. You know, it's a super common misconception that the internet is just a bunch of electricity zipping through copper wires. But the true backbone of our global communications network isn't made of electricity or metal at all. It's made of light and glass. And to really appreciate this, you have to wrap your head around the mind-boggling scale we're dealing with here. We are talking about a strand of pure glass that is literally thinner than a single human hair. Yet this microscopic strand carries enormous amounts of data over vast distances with almost zero loss of signal. Now, if you look closely at how that tiny strand is structured, it's not just one solid piece of glass. It's more like a 3-layer cake. Right in the middle is the core, which is anywhere from 8 to 62 microns wide, and this is what actually carries the light. Wrapped around that is the cladding, which is a separate layer of glass designed to perfectly reflect the light back into the core. And finally, there's the buffer coating, just a protective plastic layer on the outside. But it makes you wonder, how on earth do we manufacture something this precise and this tiny? Section 2. The 5 stages of creation. The factory floor. Let's step onto the virtual factory floor. Making fiber optic cable is a highly precise sequential process. We are going to look specifically at the 5 stages of fiber creation, starting with making the preform, then fiber drawing, coating and curing, testing and measuring, and finally spooling and cabling. So, stage 1 is preform making. You might assume we just start spinning tiny glass threads right off the bat, but actually, scratch that. Everything begins with a preform. This is a solid glass cylinder, roughly the size of a baseball bat. You can think of it as a large-scale blueprint of the final hair-thin fiber. It's meticulously shaped to already contain both the core and cladding regions. To build this preform, manufacturers use a process called modified chemical vapor deposition, or MCVD for short. Basically, they pass high-purity chemical vapors through a rotating hollow glass tube that's heated by a moving torch. These vapors react and fuse onto the inner wall as layers of ultra-pure glass soot. They also add trace elements like germanium. This germanium slightly raises the refractive index of that inner glass, which, as we'll see in a minute, is absolutely crucial for guiding the light. Once the layers are built up, intense heat collapses the whole tube down into a solid glass rod. That brings us to stage 2, fiber drawing. This is where the magic of scale really happens. That heavy glass preform is loaded into a drawing tower, which is this truly impressive, highly controlled structure that can easily stand over 6 meters tall. Inside this massive tower, the tip of the preform is fed into a furnace and just blasted with extreme heat. We're talking around 2,000 degrees Celsius. That's 3,600 degrees Fahrenheit. At this temperature, the solid glass blueprint softens into a thick, syrupy-like state. Gravity then takes over, pulling a thin strand of molten glass straight down. Now contrast that blinding heat with extreme microscopic precision. As the glass is pulled, that baseball bat-sized preform is stretched down into a fiber that is exactly 125 microns thick. A laser micrometer is actually measuring this diameter thousands of times per second, adjusting the draw speed instantly to keep the thickness perfectly accurate to within a fraction of a micron. And incredibly, as it stretches, the internal proportions of the core and the cladding stay exactly the same. No way, right? Moving right along to stage 3, coating and curing. Bare glass, no matter how ridiculously pure it is still brittle and highly vulnerable to surface scratches that could weaken it. So, within literally seconds of being drawn on the tower, the strand zips through a coating cup. This applies 1 or 2 layers of a liquid acrylic polymer, which is then instantly hardened or cured using UV lamps. This buffer coating brings the total diameter to about 250 microns, protecting the pristine glass from moisture and microscopic bends right out of the gate. Stage 4 is testing and measuring. Quality control here is completely automated and happens right in line as the fiber is drawn. The machines briefly stretch the fiber to test its tensile strength. But the really fascinating part is the OTDR test. That stands for Optical Time Domain Reflectometry.
Basically, they fire a pulse of light down the brand new fiber to analyze the reflections. This detects any hidden breaks, inconsistent attenuation, or microscopic defects along the entire length of the newly drawn glass.
And finally, stage 5, spooling and cabling. This is where we wrap things up. The finished, flawless fiber is wound onto massive spools that hold many kilometers of continuous strand. From here, multiple fibers are bundled together. They're wrapped with strength members like aramid yarn, enclosed in a protective jacket, and sometimes even heavily armored. This whole process transforms that delicate 125-micron glass into the rugged, finished fiber optic cables we bury underground, snake through buildings, or literally drop to the bottom of the ocean.
Section 3. The physics of light. Bending the beams. All right, so the factory tour is complete, but how does this finished cable actually transmit a text message across the globe? Well, it all comes down to an incredibly elegant rule of physics: total internal reflection. Remember in stage 1 when I mentioned they add germanium to the core to change its refractive index? The refractive index is just a measure of how much a material bends and slows light. The core's index is deliberately kept slightly higher than the clottings. Because of this, when light traveling through the core hits the clotting boundary at a shallow angle, it doesn't just pass through, it reflects entirely back into the core. So picture the light signal literally zigzagging down the core. The boundary between the core and the cladding acts exactly like a perfect mirror. This total internal reflection repeats thousands of times per meter. It allows the light, which is really just rapid pulses of ones and zeros sent by a laser diode, to bounce down the entire length of the fiber with minimal loss, effortlessly following the glass even around gentle bends.
Section 4. Single versus multi-mode. Choosing the right fiber. Now, it's pretty important to point out that not all fiber is created equal. The specific real-world application totally dictates the core size used in the manufacturing process we just discussed. The two main players are single mode and multi-mode. Single mode has a microscopic core of just 8 to 10 microns. It only allows one single light path, which prevents the signal from spreading out. This makes it absolutely perfect for cross-country telecom and massive internet backbones. Multi-mode, on the flip side, has a wider core of 50 to 62.5 microns. Light spreads more over distance here, so it's strictly used for shorter runs, like connecting servers inside a single data center. Plus, it's cheaper to connect because that wider core is simply an easier target to hit with a laser.
Section 5. Why fiber beats copper. The ultimate connection.
After seeing the intense 5 stages of fiber creation, you might be asking, why go through all this trouble? Why stretch pure glass at 2000 degrees Celsius instead of just using standard electrical copper wire? Well, the advantages are staggering. First, speed and bandwidth. By using different wavelengths of infrared light simultaneously, pulses of light carry exponentially more data than electrical signals ever could. Second, distance. Thanks to low attenuation in the glass, light signals can go much further without needing a boost. Third, immunity. Glass isn't metallic, so light just ignores the electromagnetic interference that constantly disrupts copper lines. And finally, security. A fiber optic cable is incredibly difficult to tap into without physically breaking the glass, which immediately trips the system and gets you caught red-handed.
Which leaves us with this final thought. We rely on the internet every single day, right? We completely take it for granted. But knowing the extreme 2000-degree heat, the insane microscopic precision of the drying tower, and the brilliant physics of total internal reflection, how will you think about the internet the next time you send a simple text message across the globe? It's pretty wild to realize that your words are literally turning into invisible infrared light, quietly bouncing off microscopic glass mirrors beneath our feet and all the way across our oceans. Thanks for joining me on this explainer. Keep learning, and I'll catch you on the next one.